Hey guys, welcome back. We're going to talk about molecular structure and acid-base strength. All right. So we think about strength of an acid, right? When we talk about our strength of a base, we're really talking about the size of K, right? How far the reaction proceeds, or how much does H plus ionize? That's the question, right? Well, two factors affect strength. Right now, there's two factors, and there's two different classes of acids we're going to talk about here. We're actually going to talk about three, but right now we're going to talk about two. So we're going to have binary acids, which is HA. Doesn't matter what A is, HA, right? Then we're going to have ternary oxyacids. H bonded to O bonded to a central atom. Now they're typically written HYO, right? But it's HOI. All right, so if we talk about binary acids first, we're going to zoom in on binary acids. The first factor would be the polarity, bond polarity, all right, of the bond between H and A. I want to know how polar that bond is. All right. As bond polarity increases, all right, acid strength increases. All right. And so, for example, all right, we have CH4, NH3, H2O, and HF, right? And so we go from not polar to very polar. Okay, and of course we are acidic here. We are slightly acidic. And then we are not acidic here. Right? So as we get more polar, we're more likely to be an acid. That's number one. Number two, all right, the bond strength. Of H bonded to A. All right. And kind of makes sense. The weaker the bond, the stronger the acid. Right? And so if we have a couple acids here, HF, HCl, HBr, HI. So the halogens, right? We already know that HF's a weak acid, and HCl and HBr and HI, hydrochloric, hydrobromic, and hydroiodic, are strong acids. Let's talk about the bond strength. So we have 570 kilojoules per mole for hydrofluoric acid, 431 kilojoules per mole, and then 366 kilojoules per mole, and finally 298. So this is a weak acid, and these are strong to strongest. All right. So that's how, for binary acids, that's how we can predict how strong the acid is. The bond polarity and the bond strength. Okay? Ternary oxyacids. All right? And I'm going to switch to blue to write this so you can clearly see the difference. The first factor, right, would be the electronegativity of Y, the central atom. Right, the central atom. That's what we're worried about here, right? So as the electronegativity of Y increases, all right, acid strength increases. Well, what do I mean? So if we have H, right, OI, HOBr, and HOCl. Now, typically they're not going to be written this way. They're going to be written HIO, HBRO, and HClO, right? And so for naming purposes, hypochlorous acid, hypobromous acid, hyperiodic acid. All right, so the electronegativity of the central atom. So for I, it's 2.5. For bromine, it's 2.8. And for chlorine, it's 3.0. All right, and then it gives you a Ka value. All right, for acid, Ka, make it nice and so you can see. Ka, we got 2.3 times 10 to the negative 11th versus 2.0 times 10 to the negative 9th and 2.9 times 10 to the negative 8. And so if you look at this, they're all very small numbers, but they're all basically the same number. 2 times 10 to the right. So negative 11th to negative 9. That's 100 times, right? This is 100 times bigger. This is 10 times bigger, right? Okay, so just to put that in perspective, it's a huge difference. Just imagine if your next paycheck was 10 times bigger. That's a big amount. It doesn't matter what your paycheck is. It could be, $100. If it's 10 times bigger, that's huge, right? If it's 100 times bigger, it's ridiculous, right? If you had a $100 paycheck and it was 100 times bigger, that would be amazing, right? Okay, it's a huge difference, all right? So that's how the electronegativity of the central atom matters. Now, the second factor, right, would be the number of oxygens bonded to the central atom. Now, let's give it space. This leads us to the oxidation state. All right, so for example, what we need to know is that more oxygens equals more acidic. And so we'll just take the chlorine oxyanions. Hypochlorous acid, chlorous acids, chloric acid, and perchloric acid. All right, the oxidation state. +1, +3, +5, +7. Ka. So hypochlorite, chlorous acid is 2.9 times 10 to the -8 again. Chlorous acid is 1.1 times 10 to the -2. Again, that's a million times stronger. All right. Around 1 for chloric acid, which chloric acid is more of an oxidizer than an acid. It's good. And then we're just going to put large for perchloric acid. I don't know what it is. It's big. We just assume it goes to completion. All right. So those are the factors that affect the strength of these acids. Now, there's another class of acid that we need to talk about, and these are the organic acids. What are organic acids? Right? Because if we look, I have H, I have O, I have I. All these are nonmetals. So organic acids typically have carbon in them. All right? Carbon containing. All right? Mainly carbon containing. All right, and so we got carboxylic acids. All right, I have my carbon here, and then we'll have oxygen, and your hydrogen. So when you look at this, and a lot of times they just put R here, because it doesn't matter what R is for like the rest of the compound. And then you have the carboxylate anion. Right. You still have carbon here. You still have your oxygens and R. But we just have a lone pair here, and it's minus. Okay. Now, how we change these, make them more acidic, right, is putting more electronegative atoms, all right, I'm just going to put 4R. Doesn't matter what R is. That's going to be more acidic. All right. So if we remember this from Chem 1, okay, there's no resonance here. There's resonance here, right? What do you mean? That means that the double bond can go here, right? And these lone pairs can kind of go back and forth. So these electrons are just resonating between these three atoms. It's resonance, right? The whole thing is negative, but this is where the electrons are going. That's the negative side. Resonance stabilizes the molecule, right? Here, we got hydrogen not being shared very well with oxygen. And so R, the more electronegative R is, the more it's pulling electron density towards itself, the weaker this bond is. All right? What do we mean by that? So we have CH3 as R, and then you have your COOH, right? That, acetic acid. If we make it RCCl3, COOH, chlorine is way more electronegative than H. So that's going to pull electron density towards R, right? Because remember, this is R, that is R. Okay? And so chlorine is going to pull electron density towards itself. So if I have Cl's out here, right, Electron density is coming this way. All right. Now, oxygen is still trying to pull it back, and oxygen doesn't want to give it up. And oxygen is very electronegative. All right. And so oxygen pretty much kicks off that H and takes these electrons for itself. All right. To get this resonance going here to make it more stable. So that's why more electronegative atoms for these carboxylic acids produce stronger or more complete ionization for these carboxylic acids. All right. Well, hopefully that works for you guys. If you have any questions, reach out. Otherwise, we'll see you next time.